All right, so graphing. Graphing is crucial for science because it allows us to represent our data in a kind of quick reference visual fashion. Um, Having a chart just full of data, okay, numbers, that represent something, is not always, doesn't always make it possible for people to easily see the relationship that you've discovered between two things, right? Having a graph allows us to very quickly see what the relationship is between two variables. So for example, the graph that's on the board right now is a graph that is relating the effect of temperature on the rate of photosynthesis. All right. Now, just looking at that graph, I can tell that temperature affects photosynthesis. Agreed? Okay. And I can tell pretty quickly that there's kind of a tipping point for that relationship as well. It generally goes up. So increasing temperature increases the rate of photosynthesis until what? What's the tipping point? 30 degrees Celsius. Yeah, clearly here at 30 degrees Celsius, okay, anything above 30 degrees Celsius clearly does not have a positive effect on photosynthesis. So I can, without having to read somebody's big, long report about the research that they've done for the past 20 years on temperature and the rate of photosynthesis, I can look at this graph and go, oh, temperature affects photosynthesis positively, but if it gets too hot, photosynthesis essentially stops. Okay, once the temperature reaches about 37 degrees, the rate of photosynthesis drops to zero, and a plant is just not doing it anymore. Right? And that seems to be fairly clear from that graph. Okay, so the purpose of a graph is to quickly relate your data in a way that people can, I guess, quickly analyze, as opposed to having to read a whole bunch of stuff about what you've discovered. Not that all the other stuff you write down isn't important, but this is the quick reference. Okay. Another example could be, maybe I've just come into some money, okay, and I want to invest it. Okay, so I'm looking at these, stocks and whatever, that I could put my money into. If I'm looking at, okay, the price of stocks and time, and I'm comparing these two stocks, which one do I want to put my money in? The red one. Okay, because the red one's going up. I don't want to invest my money in the blue one. That business is tanking. It's like Toys R Us. Okay, well, yeah. Unfortunately, that's a low blow. But okay, they bet on the Last Jedi toys, and nobody wants that junk. So bad business model. Okay. Anyway, graphs provide us a quick reference. Okay, they tell us information fairly quickly. Right? Do we want to rely entirely on the graph? No, there could be extenuating factors that cause all of this stuff. Okay, online shopping has certainly affected Toys R Us's ability to compete in a modern world. Okay, I don't know that by looking at the graph, but maybe there's something in the report about that, and it's still important to go through and read all the other stuff. Okay? But that's the purpose of a graph. Now, for a graph to be effective, it needs to have structure, okay? And actually, both of these graphs are missing something very important. What does neither one of these graphs have? Okay, yeah, neither of them has a title, okay? And this one, the photosynthesis graph, doesn't have a unit for the rate of photosynthesis. I don't know what that, it's probably in like milliliters of oxygen produced or something like that, but it doesn't say that here, okay? So yeah, we definitely want to have a title, okay? Every graph should have a title, and every graph should have a Y and an X axis that are labeled so that I know what's on each axis. Okay, you'd be surprised how often people hand in graphs to me on lab reports and they look like that. And I'm like, what is that? What is that a graph of? Okay, I mean, they would have numbers, okay, but the numbers don't mean anything. I don't know what's on each axis. I don't know whether they put the data on the right axis or not because they didn't label it. They didn't give it a title. Okay, that could be a graph of an ant walking in a forward direction, or it could be a graph of, temperature of a burner after I turn it on. I don't know. It could be anything that's showing an increase over something else. I don't know. Okay, it has to have a title. It's got to have axes that are labeled. Okay, all of that kind of stuff. So those are things we want to make sure we include on a graph. Now, the x-axis is always our horizontal axis. Which of our variables should go on the x-axis? Manipulated, responding, or controlled? Manipulated. Okay, your manipulated variable always goes on the x-axis. Okay. Okay. The reason for that is I want to be able to show people what the change I made or how the change I made affected what goes on the y-axis, which would be the which variable? The responding variable, right? Okay, so the y-axis will have the responding variable. Okay, so obviously in this graph here that we looked at the beginning, temperature was the manipulated variable. This person had an experiment, likely where they had plants that were all identical, okay, that they were giving the same amount of water to, all of that kind of stuff that doesn't show up on the graph. Controlled variables never show up on a graph because they don't change, okay? So they were graphing and they were measuring, I don't know what, the rate of photosynthesis somehow. I would assume it's milliliters of oxygen produced, okay? They were measuring that as a function of temperature. Okay, so they probably had plants in different areas where the temperature was the same, or sorry, where the temperature was different, but everything else was the same, and they were just measuring that. Okay, everyone all right with that idea? Okay, so what we need to understand here is that, yes, we've got to have that stuff. Our axes need to be labeled. They need to have units. Okay, because otherwise, and I've seen this actually happen on a graph, okay, somebody had a graph like this, and it was like, it had a good title, it was like dog running or something like that. Okay, and they had time down here, and then they had distance here, and the distance was not, or sorry, the distance was in kilometers. Okay, the distance was in kilometers, and the graph looked like this. And they had the numbers. Okay, so they had the numbers like this. So it's like 1, 2, 3, 4, and 5. And then they had 1, 2, 3, 4, 5, 6, whatever. Okay, but they didn't put any units on the x-axis. So I said, okay, is this like Bolt? Because I don't know. If the time's in hours, then this dog is, you know, an average speed dog. Okay, and it's maybe not even really running all that fast. He's just kind of jogging. But if the time's in seconds, this is Bolt. Okay, like this dog runs at supersonic speed because he travels 1,000 meters in a second. Right? It can be very misleading if I don't have units on my graph, and it can lead people to incorrect conclusions. Okay, so we need to have units on both axes. All right, so I'm going to show you how we're going to do that in Google Sheets with some kind of simple graphs. Okay, all right. Now, other things we need to know about graphs, okay, is that the graphs we're going to build are going to be simply line graphs. So most of you have probably taken this in math already. If I have a line graph like this, there's an equation that represents that line, right? That equation would be this. Y equals m times x plus b, all right? That's the linear graphing equation, okay? Y represents the y value of any point that is on the line. It has to be on the line. It can't be a point that's not on the line. Okay? X represents the x value of that same point. What does B represent? The y-intercept. What's M represent? The slope. Okay? So M is the slope of the line. Slope is probably the most important thing we get from a line on a graph because it tells us the relationship between the manipulated variable and the responding variable. If this is a graph like the dog running, okay, but it's instead of kilometers and hours, it's in meters and seconds, okay? The slope of this line will tell me the speed of the dog because it'll tell me how many meters they go every second, okay? Everyone follow me on that? Right, so the slope, okay, if I want to calculate m, get it by itself, I'm going to subtract b. I'm going to go y minus b divided by x equals m. Right, so essentially what I'm doing is I'm taking y, I'm subtracting b, so I'm finding out how much the line goes up, and I'm dividing it by how much the line goes over. Okay, you guys follow me there? Okay, so if I'm taking this here, this is a distance, is it not? And this is a time. So when I go y minus b, what I'm effectively doing is going final position minus initial position divided by time. That's where we get v equals d over t from. Okay? V equals d over t is the slope of the line on a distance or position versus time graph. Okay? We haven't gone over position versus time graphs yet, but that's where that formula comes from. Okay? It's just a manipulation of the slope formula. Okay? All right, so we're going to look at how we use this here in a little bit, but first let's look at just building a graph. Okay, so I'm going to sit down at the computer and walk you guys through the same thing here. Okay, but we need to go to this one here. Okay, the Google Sheets practice. This isn't coming in from Marks. We're just going to use the same file so we all get the same numbers. All right, so if you just click on that, okay, it'll have your name there. Okay, and it'll have a Google Sheet for you to open. So if you can just open that. Okay, so the first graph that you're going to have here is going to be data. I think this is for a rubber band. Still loading. The internet is blazing fast this morning. So I've got my force and length here. So what this experiment was doing essentially was it had a rubber band, and what they were doing was they were stretching it with various amounts of force and then measuring its length. Okay, so in that experiment then, force was the manipulated variable, right? Because they used 1 Newton of force, 3 Newtons of force, 5 Newtons of force, et cetera, et cetera. Oh man, sorry guys, I don't know what's. So we got, so the experiment was that we had different amounts of force and we measured the length of the rubber band. So obviously when I don't pull or stretch the rubber band, it still has a certain length, okay? And so that's what this first point here is going to be about. The rubber band, when not being stretched, is 6.5 centimeters long, okay? After that, if I start exerting force on it, obviously it stretches and gets longer and longer. So what we want to do is we want to make a graph of that where force, which we said was the manipulated variable, ends up on the x-axis, and length ends up on the y. So what you're going to do is put your pointer in the first box there where it says force in newtons, okay? And you're going to click and hold and drag until you highlight all of the data. Right? Then you're going to go to insert. Okay? And you'll see in the drop-down menu that one of the options is chart. It's about halfway down. Right? Click on that, and then it's going to, Google Sheets tries to figure out what you want. It never gets it right. Okay? So when I click on that, it's going to bring up a bar graph. Well, I don't want a bar graph for this. Okay, so what I do is I go here to chart type, and I just click on it, and I want to scroll down till I get to what's called a scatter plot. Okay, so it's a ways down. Okay, here's where we are at the start. We have to scroll down through line, area, column, bar, pie, down to scatter. Okay, so click on scatter, and you'll get the points looking like this. Now, because in our chart, we actually put in that one thing was length and one thing was force, you can see that Google Sheets even wrote on here, it labeled the axes and it put the units in for them. Okay, so I've got force in newtons down here, I've got length in centimeters up here. All right, is everybody to that point, or is there anyone who needs my help? Everyone's good there? Okay, so now that I've got that, okay, now what I want to do is I want to customize this chart because there's still a couple of things I need to put on there. Right now, like this title here isn't great. Okay, it says length versus force, but it's not really a description of what my experiment was. Right, so I'm going to go over to customize, click on that. Okay, chart style. Okay, we've already kind of done that, so we don't need to worry about that. Axis and titles. All right, we're going to click on that, and it says here chart title, and there's what it wrote in for the title. Okay, title text. I'm going to change that, and I'm going to call it rubber band experiment. And you can see that Google Sheets automatically updates that as you go along. All right, so now we've got a title that's a bit more, that tells us a bit more about what's on this graph. I already knew it was a graph of force versus length just by looking at each axis, okay? But at least now it tells me it's about a rubber band, okay? That's a little more context. Okay, then I'm going to scroll further down, okay, to series. This is where we get our best fit line, or our line of best fit, okay, depending on how your math teacher terms that, okay? So we got some options here for the points. Sometimes I make the points smaller, but I mean, for this graph, that size of point's fine. You can change the points to be whatever shape you want, squares, diamonds, X's, whatever, okay? Pentagons, doesn't matter. Okay, if we scroll a little bit further down here, you'll see it says error bars. If you click on that, it puts in these bars. They look like this. We don't ever need those, so you won't need that. Okay. You can put in data labels if you want. I wouldn't. I find it makes the graph look really busy because it actually puts in the values. Okay, and I find that that just looks busy. But this is the one we want, trend line. Okay, so I want you to check the box beside trend line. All right, and you can see it drew the line of best fit. Now, it just so happened it actually went through like every single point. That's pretty rare. Most of the time when you're using actual data, your line of best fit will be drawn so that it takes into account all the points and none of them will be on the line. Some will be above, some will be below, some will be close, but your line will always be the average, okay, or the trend of those points. All right, so now that I've got that line, the next thing I want to put on my graph is a label for that line. Okay, so you can see here where it says label, it says none right now. What I want to put on there is the equation, the y equals mx plus b equation for this line. So if I click on label, it says use equation. So just click on that and it spits out the equation for the line. Now it doesn't say y equals, but this is what y equals. Okay, everybody with me so far? All right, so I've got that graph now fully built. Okay. So now if I was putting this into a lab report, I would just click on the three dots here, okay, go copy chart, and then put it into a Google Doc. Okay, so if I had a doc open, holy smoke, so slow. So if you paste this into a Google Doc, it'll ask, do you want to link it? You do, because that way if you go back and make any changes, it automatically changes the graph in your lab report without you having to recopy and paste. Okay, so you would want to link it so that any changes you make would be changed in your final lab report. All right, so now, next thing we're going to do with this graph is we are going to do a little bit of calculating using y equals mx plus b. All right, so what I'm going to do is just take a snapshot of that. Or I already have it maybe. Okay, so there's my graph, okay? My graph of the rubber band. And I've got my equation here. So what this equation is really saying is that y equals 2 times x plus 6.5. Okay, remember that 6.5 was the original unstrained length of the rubber band. It also now happens to be what part of the equation? It's the y-intercept. Okay, it's the length of the rubber band when the force acting on it is 0. Okay, so what this equation can help me to find is it can help me to determine the length of the rubber band regardless of what force I'm putting on it. Or it can help me to figure out, if I know the length of the rubber band, how much force would be needed to make the rubber band that long. Okay? I can use this equation to calculate that stuff. So let's say that a question came up and it said, what would the length of the rubber band be with 45 newtons worth of force acting on it? Okay, so the question is, how long will the rubber band be with 45 newtons of force? So if I'm looking for length, am I looking for y or x? Y, right? Because length is on the y-axis, right? So it's asking me calculate a y value, and it told me the force. Well, force is an x value because force is on my x-axis. Right? And we said it was for 45 newtons. So what we would do is we would say, okay, y equals 2 times 45 plus 6.5. Okay, which means that the length of the rubber band, when 45 newtons worth of force is on it, is going to be 96.5 newtons. Probably would snap before that, I would think, but I mean, centimeters, sorry. I put newtons, should be centimeters. You're absolutely right. Newtons measure force, not length. Okay, everybody follow what I did there? Okay, now the opposite could also be true. They may ask me, when the rubber band is 50 centimeters long, how much force is being applied? Right, so now they've given me a y value and are asking me to calculate an x value. So now I take my equation, y equals 2 times x plus 6.5, and I'm solving for x. So if I want to solve for x, what do I do with the 6.5? I subtract it over, right? So I'll have y minus 6.5 equals 2 times x, and then I divide both sides by 2. All right, so now I'm solving for x. They told me y was 50 centimeters, right? So I'm going to go 50 minus 6.5 divided by 2, right? So that'll be 43.5 over 2, 21.75, I think. I should probably not do math in my head. I should do math in my head. Okay, 21.75 newtons of force would be required. Okay, those are the kind of things you'll be expected to do, and you would have had to do those in math. Okay, you would have manipulated this equation in math, so I'm not asking you to do anything you haven't done before. All right. Okay, everybody good with that one? All right, click on the next sheet over. Okay, so if I'm looking at that sheet we just built here, okay, that was sheet 1. I want you to click on sheet 3. Okay, sheet 3 is a chart about the thickness of a book. I want you to build the graph, a line graph, just like we just did. See how much of it you can remember, right, for that set of data. I'll give you a few minutes on that, and then I'll walk through it myself. Okay, so the super quick walkthrough of this one. We highlight everything. We go to Insert, Chart. Okay, we tell it, no, you didn't pick the right type of graph. Okay, where am I at here? That's not what I want. Oh, that's why. Okay. All right. So we got our scatter plot there. Okay. Then we can go to customize and we can give it a proper title, like, I don't know, book thickness graph or something like that. And then we'll go and get our trend line on there. We'll give our trend line a label of the equation, right? And then we're good, okay? It's all built and we're ready to go. All right, so here's what I want you now to do with that graph and the equation of that graph. I want you to answer for me these two questions. Okay, I want you to calculate how thick a book made of 1,350 sheets will be. Okay, and I want you to calculate how many sheets are in a 205 millimeter thick book. All right, I'll give you a few minutes on those. Okay, so our first question here is how thick will a book made of 1,350 sheets be? So we need to go back up and get our equation here. It's 0.15x plus 5. Okay, so that's our equation. We're looking for the thickness of the book, which is a y value, okay, because that's what's on the y-axis is book thickness, all right? They told me how many sheets it has, which is an x value, so I'm going to substitute 1,350 in for x so that I can calculate how thick the book will be at that point. So I'll have y equals 0.5 times 1,350 plus 5, okay? What do you suppose that 5 is, that 5 millimeters? Like basically we're saying that the thickness of a book with no sheets is 5 millimeters. It's the cover. Yeah, it would have to be the cover slash the spine of the book. Oh, sorry, 0.15. Sorry, you're right. 0.15x. Okay, so now we've got that. Okay, and so we'll punch it in here. So 0.15 times 1,350 sheets plus 5 millimeters. All right, so we're looking at 207.5 millimeters thick. Okay, what is the slope telling me about this book? Exactly, it's the thickness of one sheet. Okay, because it would be, if we look at the units, right? If I manipulate this equation to solve for m, okay, because we've got y equals m times x plus b, okay, manipulated for m, it's y minus b over x. Y and b are both in millimeters, and x is sheets, so it's millimeters per sheet. Okay, so that's essentially one sheet is 0.15 millimeters thick in this book. All right, question number 2 wants to know how many sheets there are in a 205 millimeter thick book. All right, so they told me y or x there. That's a y value, okay, it's the thickness. So I'm looking for the number of sheets, which is on the x-axis. So I've got to manipulate y equals 0.15 times x plus 5. I've got to manipulate that for x. So I'm going to subtract 5 from both sides. We'll have y minus 5. And then I'm going to divide both sides by 0.15. That'll leave me with x. Okay, so we'll have 205 minus 5 divided by 0.15. So basically 200 over 0.15 will tell me the number of sheets in that book. All right, so there's 1,333 sheets in that book. Okay, making sense so far? All right, we'll do one more. So this one's a position versus time graph. It's telling us where an object is at various points in time. Right? And we'll be looking at position versus time graphs quite a bit this week, so this will be a good start to that. Right? So build me another line graph of this data. Obviously, it's going to have way more points on it than the others. Okay, so we'll highlight all of it. Okay, we'll insert the chart. And obviously we want the scatter plot. Okay, and then we will go to customize. And I'll just leave the title on there for now. Okay, we'll go to series. We'll put on the trend line. Okay, and you can see on this one that this is more like what I was telling you. Some of the points don't end up on the line here. Okay, and that's because the line is supposed to follow the trend. It's the line of best fit. Not all the points are going to be on it. In fact, if we made those lines smaller, okay, or those points smaller, we would see that a lot less of them are actually on the line. Okay. All right, so we need the label here for the equation. All right, so now we've got that, okay? And as I said before, that slope, that 3.85, is actually the speed, or sorry, the velocity of this object. Okay? It's telling me the rate at which it covers meters per second. Okay? If I go y minus b, I'm taking the final position and subtracting the initial position, okay, and dividing it by time. All right, I'm taking displacement over time, and I'm getting, okay, the velocity out of it. All right, so what we're going to look at, in fact, I think we got time here to do this one. So let's bring it over. All right, so if we've got our position versus time graph here, okay, and you guys have the same one, obviously, I want you guys to calculate two things for me. How long will it take to reach a position of 208 meters? And what will the position be at a time of, let's say, 60 seconds? Okay, so if we're looking at question number 1 here, okay, we're solving for an x value, how long it will take. So we're taking our y value, 208, we're subtracting our y-intercept, but our y-intercept is negative. If you look closely at the equation, it's negative 0.801, so you have to take that into account. Okay, so we're looking at 208.801 divided by 3.85. All right, so it's going to take 54 seconds for it to do that, 54.2 seconds. And then if we're looking for the position, okay, of the object after 60 seconds, y is going to equal 3.85 times 60 plus negative 0.801. All right, so all right, 230 meters, okay, would be our position at that point. All right, we'll talk more about that stuff tomorrow. If you can put those Chromebooks away, guys, that'd be great.